Good morning, everyone, and welcome back to Math 115. Today we are going to be talking about section 2.3, and I'm going to do my darndest to make it all the way through 2.3, if I can. Okay, so let me first remind you that you have two homework assignments due tomorrow at 11:59 p.m. That is 2.1 and 2.2, which we finished yesterday. So your next assessment, okay, is going to be quiz 4 on Tuesday. So that is going to cover everything up to what we talked about yesterday. So 1.6 to 2.2, okay, so that's library of functions, transformations of functions, compositions of functions, inverse functions, quadratic functions, and polynomials. That's what will be eligible for the quiz. So as always, the quiz questions will be pulled directly from the homework, word for word. I'll make the numbers nice so that you don't need a calculator, but you might need to multiply or divide things up to like 12 times 12, right? Something like that. Okay, so regarding the quiz, there will be a review today in office hours from 2:30 to 4 p.m. Can I have a show of hands who is planning on coming to office hours today? Okay, that's like 10 or 12 people that I see immediately, so we're definitely going to move rooms. So I will plan on probably going to LeConte 109. I think that's the room that is usually available at that time. But I will send an email, so just keep tabs on your email. If you don't have email on your phone, what are you doing? Just get it on your phone. No, just kidding. I'm not going to judge you for that. But
question.
Yes?
I don't get the emails for like when teachers cancel classes, like so I always just show up. Wait, why? I don't know, like it's in like my quarantine messages. And like I don't know how to get it out.
From Blackboard?
Yeah, they like do like an announcement or something, or like just like a normal email out. Like I just.
Okay. Well, then what you can do is I always post the announcements via the announcements tab on Blackboard. Okay. So if you go to our Blackboard homepage, you will see the announcements. Okay. Here. And if you click on those, they'll show you my emails that I send out as well. So that's another method. Does that make sense?
Yeah.
Okay. So yeah, if you can't see my emails, that's another place you can see my messages. Okay, so that's about the quiz. So again, office hours today, 2:30 to 4 p.m., probably in LeConte 109, but I will make sure to put a sticky note on my door, on my office door, and I will send out an email if we change the room. So if you can't make it to office hours, go to the tutoring center. I say that every single time. Okay, so let's start by reviewing what we talked about last time, which was basically everything past the intermediate value theorem. So I'm not going to repeat my spiel on the intermediate value theorem today, but if you're still a little bit confused about it, let's talk about it in office hours. So we talked about the number of zeros that a polynomial is going to have, and well, we're going to expect it to have at most n real zeros. At most n real zeros if it is a polynomial of degree n. And moreover, this counts multiplicity, right? So what was multiplicity about? It was the power with which the factor appears in the factored form. Okay, so here x squared is a zero of multiplicity 2, and the others were multiplicity 1, right? Okay, so next up we learned about turning points. So again, with the function, a polynomial function of degree n, it is going to have at most n minus 1 turns, right? So think about like a cubic polynomial probably looks something like this. Okay, cubic polynomial looks like this. How many turning points? 1, 2. Okay, that's the most that a cubic polynomial could have. Or think about a quadratic polynomial. How many turning points does it have? Just 1, right? Okay, so it's at most 1 less than the degree. And then we talked about how to sketch, okay? So we talked about when are we going to pass through the x-axis at a 0, when are we going to bounce off the x-axis at a 0. Well, that's when the multiplicity is either odd or even, respectively. And if it's odd and larger than 1, we don't just go straight through. Actually, what we do is we kind of flatten out, kind of like the graph of x cubed for a second, and then go through. Okay, so that's how you can get it to look a little bit better. So then we use basically all of these things that we had learned in this section to try graphing some polynomial functions. So we did that using basically 3 things. The end behavior, okay, so talking about the limit as x goes to infinity or minus infinity, which was determined by the leading term. And then we checked the zeros, and we looked at their multiplicity, right? So to check whether they're going to pass through or whether they're going to bounce off, right? Was there a question? Okay, so then we want to find their y-intercept, okay, and that's going to tell us where we pass through the y-axis. Okay, so then once we had all that information, we were able to sketch the polynomial. It's not going to be perfect, but it will be pretty good. It will have the features of this graph, namely that it will pass through 0 at the relevant spots, and it will turn around in the relevant regions, okay, and the end behavior will be correct, okay? So it's not perfect, but it's pretty good. So let's start. We're not going to do partner work with this one, but I'm going to quickly go through this example one more time for us so that we can see what's going on here. So the number one thing I care about if I want to sketch this is end behavior. Can someone help me with the end behavior? How am I going to check it? How do I figure out whether the function's like down and then up, or if it's like, you know, down and down on the ends? How do I figure that out? Yeah, Andrew? I need to get the leading term, right? So I could go ahead and FOIL all of this crap out, okay? But we can also see generally, okay, what the power of each thing is going to be, right? This represents a cubic polynomial. This represents a degree 2 polynomial. If I multiply those together, what's the degree going to be? 5, right? We just add the degrees, okay? And then I need to multiply once more by negative x, right? So that would be a degree 6. So x to the 6th, and something I'm missing here? It should be negative x to the 6th, right? Because this is a negative x. So this is the leading term, which is the only thing that matters for figuring out the limit as x goes to infinity of f of x. Okay, so when x gets really, really big, what happens to x to the 6th? It'll be even bigger, right? But negative. So what is the limit as x goes to infinity of f of x? Negative infinity. And do I need to check carefully what the limit as x goes to negative infinity of f of x is? I claim no, and it has to do with this power here. Someone explain that for me? It's an even power, right? So I know that the end behavior on both sides will be the same. Okay? But if you want, you could also imagine, okay, if I plug in negative infinity, then I plug in negative infinity, I get something like negative infinity, all to the 6th power. Well, if I take a negative number to the 6th power, what am I going to get? I'm going to get negative infinity, okay? Because when I do the 6th power on this guy, it's going to cancel out this negative sign here, okay? All right. So I get negative infinity again. So that's the end behavior. Now let's talk about the zeros. Well, I have the 0 x equals to 1 with multiplicity 1. I have x equals negative 2 with multiplicity 3. And I have x equals 3 with multiplicity 2. Yeah? Anything else I should check before I get to sketching? Yeah, there's one more thing, right? What is it? The y-intercept. Very good. Okay, so last thing is the y-intercept. How do I find the y-intercept of a function f of x? I plug in 0 for x. So f of 0 would be what? Well, let's copy this function down, and I'll imagine what would happen if I were to plug in 0 for x. Well, this one would just become 1, right? So that's 1 times this one would become 2 cubed. And then the last one would become negative 3 squared. Yeah? So this would be 8 times 9, right? Which, if I remember right, is 72. Yeah? Hopefully that's correct. Otherwise, that'd be really embarrassing. Okay, so that's all the things that we need to check. So let's go ahead and do the graph based on this. Let me add a page. Shit, put the page in the wrong spot. There we go. All right, picture time. So I'm going to put a 0 at each of these zeros. So I need one at 1, and one at 3, and one at negative 2. Okay, and what else do I need? I need the y-intercept, which is 0, 72. Yeah, so it's somewhere way up here. All right, and now I need the end behavior, right? The end behavior says down on both ends, yeah? Okay, so now I just need to go from left to right, and I need to either pass through or bounce off depending on the multiplicity of each 0. So, well, you can tell I'm going to have to pass at negative 2, right? Because I need to make it up to 0, 72. So let's double check, though. X equals negative 2 has multiplicity 3. So that is an odd number, so we will pass through the x-axis. But we're going to do so in a kind of flatten out way. We'll flatten out a little bit as we get here, and then we'll start going back up again like that. And then we need to make it all the way up to 72, right? And then I don't know what happens. It might be that it turns before we get to 72, or it could be that it turns after we get to 72. It's not really clear. But we're just drawing a picture here, so we're going to do it the best we can. It's probably going to be something like that. Okay, and then what happens is it has to turn around because it needs to come down to 1, where it is going to do what at x equals 1? Pass through or bounce off? Pass through, right? Because 1 is an odd number, so it should pass through. So it's going to come down and then go through, and then it needs to turn around at some point and come back to 3, and you know already what's going to happen at 3, don't you? Because later we're going to be going down, so there's no way for that to happen if we go through. Why couldn't we go through? Because if we went through and then later we end up going down, then we would have to again pass through the x-axis, right? At somewhere like x equals 4. But we know that x equals 4 is not a 0 of this function, so that can't happen. But also we know that x equals 3 has multiplicity 2. So all of this stuff is working together in order to make sense. It kind of all... You can look at this in like multiple different frames of reference. So x equals 3 has multiplicity 2. I know I need to bounce. Okay, so now we're happy with the picture of this function. And that's not perfect, but it has the most important features of this function. All right. Thanks for that reassurance, Griffin. All right, so what should we do next? We should talk about 2.3. Unless there are any questions on this example. Let me pause and ask. Are there any questions on this example? All right, doesn't seem like there are. So we'll move on to section 2.3, which is all about dividing polynomials. So if you remember your high school algebra class, or Algebra 2 or something like that, you probably saw some kind of polynomial division, and you may have hated it. But I'm going to do my best to present it in a way that it's as clear as possible so that you don't hate it anymore. So let's talk about how we divide polynomials. So first of all, okay, we call d of x a factor of another function f of x if f of x can be written as the product of d of x times q of x. So, for example, if f of x was x squared, if f was x squared plus 2x plus 1, you could rewrite that as x plus 1 times x plus 1, yes? Where x plus 1 is our d and x plus 1 is our q. So you would call the factor, you would call x plus 1, which is the d, okay, you would call that a factor of f, right? So this is nothing new. This is just like what we've already been doing, right? So if we can pull off a polynomial, factor out a polynomial, then we call that polynomial a factor of the function. So nothing crazy here. But if you were to say that this was true, right, that f of x is equal to d of x times q of x, you could also divide both sides by d of x, yes? You could divide both sides by d of x. Okay, and this is how we would define division. Okay, this is how we define division for polynomials. So we say that f of x divided by d of x is equal to q of x, provided that if I multiply both sides by d, I get something like this. Okay? So again, division is just fancy multiplication, right? That's all that it is. Okay, so you might ask, what is the point of all of that? Well, I guess the point is to say basically that we can divide polynomials in the same way that we can divide numbers, right? There's nothing different going on here. This is the exact way, you probably don't remember, but this is the exact way that division was defined when you were in like elementary school for numbers. Okay, so that's polynomial division. So now let's talk about the division algorithm. Okay, so algorithm is just a fancy word for process, or it's a fancy word for like a list of instructions, okay? All right, so first we say, okay, we need two polynomials so that we can divide them, right? And if I want to divide f of x by d of x, right, then d should have lower degree. Okay, why is that important? It's the same reason why if I want to do like a divided by b, then this fraction would be improper, or rather, okay, what do I want to say? What I want to say is if I want to divide a by b, okay, then it needs to be that the number on bottom is smaller than the number on top if I'm actually going to do the division, right? I need something like 6 divided by 2, right, so that I can get 3, yeah? So the number on bottom needs to be smaller, yeah, in order for us to do the division properly, right? If I have 2 over 6, right, well, I can simplify, but I can't actually put 6 into 2, can I? I can't put, there's no amount of times that 6 divides evenly into 2, okay? So when we talk about doing division with polynomials, there's something similar, right? If we want to simplify something like this, we need the bottom number to be smaller than the top number. For polynomials, what that means is that we need the top polynomial to have higher degree than the bottom polynomial, right? We already saw that this would be equal to what? X plus 1, yes? Because if you moved this over, that would be the factored form of this quadratic. So we need the bottom polynomial to have smaller degree if we're going to perform this division. Okay, otherwise we just start we're kind of done right when we start. Okay, so if the degree is less than the degree of the denominator is less than the degree of the numerator, then we can find unique polynomials q and r such that f of x divided by d of x is equal to q of x plus r over d. Okay, so this is analogous to the remainder version of division. So let's see this, for example. If I were to do 7 divided by 2, what would I get? I would get 3, because 2 goes into 7 3 times evenly, and then I'd get plus a half, yeah? Plus a half. Okay, so that's like here's my f, okay, is like 7, right? My q is the number of times that the denominator goes into the numerator evenly. And then I have some left over, which I express as a proper fraction, okay? A proper fraction. So r of x, namely, should be either 0 or has degree smaller than the denominator, right? So we start with the degree is bigger here and degree is smaller here, right? So that's when we are allowed to do division. And then we end when we end up with a fraction which does not satisfy that, right? We end when we get something where the degree on top is smaller than the degree on bottom. Not 0, but degree is smaller on the top and bigger on the bottom. And that's a point where we're not allowed to do any more division, right? Because think about it, 2 cannot go into 1 evenly, so I stop there. Okay, so I'm just drawing all of these connections back to regular division because I want you to see how things are very much analogous to that. Okay, so let's see the actual process. So this is a process called long division. If you learned how to do synthetic division, you can do synthetic division. That's fine, but I'm not going to be teaching it because I think that it's just extra steps. It's just extra steps. Okay, so let's see what we do for the long division algorithm. Okay, so we're going to have like 4 steps. Okay, we have 4 steps. Not too bad. So how do we start? Well, we put the dividend, the dividend goes underneath our division symbol, and the thing which we are dividing by is called the divisor. So this is the divisor, and this is the dividend, and then at the end, what goes on top is going to be called the quotient. Well, it's the part of the quotient here. Part of quotient. Okay, so this is where we are going. So let's start. Well, the very first thing I do is I put the dividend under the division symbol and I put the divisor outside. That's pretty simple. So then what I want to do is, if there are any missing terms, okay, in my polynomial, then what I need to do is add them back in, okay, as a 0x squared and a 0x, okay? So that's all I'm doing there. I'm just doing that because this is kind of like when you're doing division, you need to be careful about the 10th place, the 100th place, the 1000th place, and so on, right? So in polynomial division, we need to care about the x cubed place, the x squared place, the x place, and the 1 place, right? So we need to write out all of those missing terms, okay? Because here's how this is going to work. What we are going to do next, okay, is we're going to look at the leading term of the dividend and the leading term of the divisor. And I'm going to divide them. I'm going to take x cubed and I'm going to divide it by x. Of course, if I do that, I will get x squared, right? If I take x cubed divided by x, I get x squared. So I'm trying to put x minus 1 into this polynomial. The first thing to do is figure out how many times does x go into x cubed. And it goes in exactly x squared amount of times. Okay? So we are very intentionally producing this expression, x squared, by dividing the leading term of the dividend by the leading term of the divisor. And this is going to give us the first term of the quotient. So we've already gotten step 1. We've gotten the first term of the quotient. Now, what should I do? I am going to multiply that first term in the quotient. I'm going to multiply that by our divisor and subtract it. Okay, so let's see how that works. So I take the divisor, or the first term of the quotient, which I just computed. It's x squared. and then I multiply that with the divisor, which is x minus 1. If I distribute, I get x cubed minus x squared. Yes? And all I'm going to do is I'm going to subtract that expression. And the number one mistake that I see students make at this step, or just in long division in general, is they forget we have to have these parentheses here. We have to have those parentheses there. Okay? We need to have the parentheses because we are subtracting an entire polynomial. Okay, we're subtracting an entire polynomial. If we subtract an entire polynomial, we need to distribute that minus sign, okay, onto each term. So now all I'm going to do is perform this subtraction. So if I were to distribute this minus sign, I would get something like minus x cubed and then plus x squared, right? If I distributed that minus sign. So I take x cubed, and hey, look, I'm subtracting x cubed. So the x cubed goes away, right? It becomes 0. Yeah, it becomes 0. These two cancel each other out and become 0. And that's by design, okay? We chose to multiply by exactly the quantity which we would need in order to make the first term of the divisor equal to the first term of the dividend, right? That's exactly why we chose it that way. Okay, so let's finish this example off. What do we have to do now? We're subtracting x cubed, so the x cubed terms go away. And we're left with just x squared plus 0x minus 1. That's what we are left with. So now it's time for the final step. Well, the final step is really multiple steps. What does it say? It says keep going. We repeat this process with our remainder. This is our remainder for now. But the remainder still has higher degree than our divisor. So we are going to continue the division process until that is no longer true. So again, my next step is to do what? I need to divide x squared divided by x. That gives me x. Then multiply divisor by x and subtract. Okay, so here's what happens. I'm going to copy this and then paste it here. So I get the next term in my quotient is plus x. I multiply x with x minus 1. Okay, if I multiply x with x minus 1, then I get x squared minus x. Yes? Now I'm going to subtract that minus x squared minus x, and I subtract with parentheses, okay? So if I do this subtraction, oh, hey, look, we chose the divisor, or this term of the quotient, precisely so that these two would cancel. This is how I chose the divisor, or the quotient. So I cancel those, and I'm left with x, because I am subtracting a negative x from 0x. So that means I'm adding x. So I'm left with just x, and then, sorry? Yeah, the minus 1 is still here, exactly. So I bring this minus 1 down as well. It's still here. It's unaffected by this subtraction because there's no term in this polynomial with degree 0. Okay, so now we're all the way at the end, okay, except I have one more step left to do. And that is because the remainder here does not have degree less than our divisor yet. it has degree equal to our divisor. And in fact, it actually is our divisor, isn't it? It is our divisor. So the next step is going to be what? I'm going to add the next term of the divisor, or the next term of the quotient, which should be whatever I need to put here needs to be whatever I get when I take x divided by x. Well, x divided by x is what? 1. Yeah, x divided by x is 1. I'm not confused about that, but I am thinking about this polynomial division. We started with x cubed minus 1, which has roots 1 and then some complex roots. Okay, so this is fine. I'm just checking to see if I made a mistake somewhere along the way. I don't think I did. So now we get a plus 1. And then what happens? We subtract from the remainder the expression x minus 1. And if I subtract x from x, I get 0. And if I subtract negative 1 from negative 1, I get 0, right? So my remainder is 0. So it turns out that x minus 1 divides evenly into the expression x cubed minus 1. Okay, so at the end of the day, x cubed minus 1 divided by x minus 1 is equal to the polynomial x squared plus x plus 1. So how could I check my work? Well, I could just take this over to the other side and FOIL, yeah? Well, not FOIL, but you have 3 terms, right? So it'd be like a 6-term FOIL, yeah? That's how I could check my work. But it's kind of easy to see that this should divide evenly into x cubed minus 1. Why should x minus 1 divide evenly into the polynomial x cubed minus 1? Why should we expect this division to work out so nicely? Well, if I did x minus 1 cubed, remember, I would need to write that out as x minus 1 times x minus 1 times x minus 1, and I need to FOIL twice. So actually, x cubed minus 1 is not equal to this, okay? This is not the same thing as well, this is the same thing as this. No, it's not the same thing as this. That's what I'm trying to say. That's the whole point. These two things are not the same, right? Okay. But why should we expect x minus 1 to go into x cubed minus 1? Well, it has to do with that list of equivalent statements. Remember, we said if c is a 0 of f of x, then x minus c is a factor, yes? So the reason that I expect x minus 1 to divide nicely into this polynomial x cubed minus 1 is because I know that x minus 1 is a factor of x cubed minus 1 as long as 1 is a 0 of the function x cubed minus 1. And it clearly is, right? If I were to plug in 1 here, I'd get 1 minus 1. Well, 1 cubed minus 1, which is 0. So because 1 is a 0, 1 is a 0 of the function, I know that x minus 1 is a factor of the function. So this is why I expect this division to go nicely. Okay, so we covered basically the entire division algorithm. Let me go over it one more time. First, we write the dividend with all the missing terms. Then, we divide the leading term of the dividend by the leading term of the divisor. Okay, so that means we take x cubed, we divide by x. That gives us the first term of the quotient. Okay, Then what do? We multiply the divisor by the first term of the quotient and subtract. Multiply the first term of the quotient with the divisor and subtract. And we always have to subtract with parentheses. Then we repeat the process with our new remainder. Okay, so we call this the remainder. And as long as the remainder has degree larger than the divisor, we're going to keep going. Larger than or equal to. We're going to keep going. So this should actually not be less than or equal to. It should be less than, I think. So we repeat until the remainder has degree less than the degree of the divisor. So we just keep going and going and going and going. Should it be less than? Yeah, it should be less than. Okay, so, and then we just keep going and going and going until we're done. So, any questions on this long division process so far? All right, let's see some thumbs. Who feels pretty good about long division and who feels not so great about it? Thumbs up if you feel like you're ready to do the homework. Okay, some down and some to the side. That's totally okay. I think this is confusing until you get the hang of it. Okay, it's confusing until you get the hang of it. So let's try another one. So we'll do this one from start to finish. Okay, so what should be my first step? What should be my first step? Before I even do any dividing of anything, what do I need to do first? I need to fill in the missing terms. What are my missing terms for this dividend? Yeah, I need to have one in between x to the 5 and x to the 3. And I need to have one in between x to the 2 and x to the 0. Right? So I need to rewrite this whole thing. I need to rewrite this whole thing, but I am going to move everything over so I have space for the plus 0x to the 4 term. And I'm going to move everything over here so that I have space for the plus 0x term. Okay, now I have all of my pieces. So I'm going to change that to be all the same color. Okay, now I can get started, right? And really, all I need to worry about, I don't need to worry about the rest of this polynomial, do I? I just need to look at the leading term and the leading term. That's the only thing that's going to determine my first term in the quotient. So what should the first term in the quotient be? X to the 3rd, right? Because that is what I would get if I did x to the 5th divided by x squared, right? We would subtract the powers, and I would get x cubed, yeah? So that's how I get this term. So then what do? I multiply x cubed with this polynomial, and I subtract. So I'm going to just multiply it straight for each of these, okay? Because I know I'd have to distribute. So I get minus, this becomes x to the 5th. If I multiply x cubed with minus x, I get minus x to the 4th. And if I multiply x cubed with 1, then I get plus x cubed. And I'm going to subtract all of that. And when I do so, I eliminate the x to the 5th terms. And I'm left with minus x to the, no, plus x to the 4th, right? Because minus minus. And then plus 3x cubed, okay, because I do 4x cubed minus x cubed. That gives me 3x cubed. And then I bring the rest of it down. Plus 2x squared plus 0x plus 7. So, am I done? No. Why am I not done? Yeah, I think Andrew said it. The degree of my remainder is still larger than the degree of my divisor. So I'm not yet done. Okay, let's keep going then. What's the next term gonna be?
X squared.
Yeah, x squared, because that's what I get when I do x to the fourth divided by x squared. I get x squared. So this is exactly what I need to put as the next term of my quotient in order for those terms to cancel when I subtract. So next up comes minus, I put a parenthesis because I always need that parenthesis, don't I? And I'm going to multiply x squared times each of these terms. If I do that, I get x to the fourth minus x to the third plus x squared. And if I subtract all of that, then these terms cancel, and I'm left with 4x cubed, because I'm subtracting negative x cubed from 3x cubed. And then I have plus x squared, because I'm subtracting x squared. I'm subtracting x squared from 2x squared. And then the rest of it just comes down, plus 0x plus 7, yes? Okay, good. So now we just have to keep doing this process over and over again. So what comes next? I take 4x cubed and I divide it by x squared. And what do I get? I get 4x. Then I multiply, I multiply, I multiply. So I get a minus sign, big parentheses, make sure we use those parentheses. And 4x times x squared is 4x cubed. Okay, hey, look, we chose this exactly so that when we multiply it with x squared, we get 4x cubed. Why do we want that to happen? We want that to happen because we want these two terms to cancel. So that's why we pick the quotient in the way that we do. Okay, so next up I need minus 4x squared, right? And then I need a plus 4x. Good. So now I just keep doing this process. I cancel, and I am left with 5x squared, right? Because I take, sorry, did I make a mistake? I think it's okay. All right. 5x squared, because I take x squared minus negative 4x squared. That means I add. Minus a negative means add. And then I have minus 4x, and then the 7 comes down, so I still have plus 7. Yeah? Am I done yet? But the powers are equal. Aren't I done? No, I have to go until the remainder has degree less than our divisor. Okay, so I keep going one more time. So what do I need to okay, what do I get when I take the leading term of this divided by the leading term of this? I do 5x squared and I divide it by x squared. I get 5, so plus 5, that's what comes next. So now I need a minus sign, big parentheses, and I'm going to take this polynomial and I'm going to multiply it by 5. So I get 5x squared. Hey, look, that's exactly what we needed to cancel those, isn't it? Okay, so then I have minus 5x and then plus 5. So finally, I do this. These two cancel. And I'm left with, okay, so negative 4x minus negative 5x means we add 5x to negative 4x, which means we get x. And then we have a 7 minus 5. So that is 2. And now I'm done. Why am I done? I am done because x plus 2 has a smaller degree than x squared minus x minus plus 1. Okay, so now I am done. So the result is the following. If I take x to the fifth plus 4x cubed plus 2x squared plus 7. And I take that polynomial and I divide it by the polynomial x squared minus x plus 1. Then the answer is x cubed plus x squared plus 4x plus 5. That was the number of times that the divisor went into our dividend evenly. So now I have this leftover bit. How do I incorporate the leftover bit into my answer? I put a plus, and then I put x plus 2. I couldn't divide it into x plus 2, so I just leave it as a fraction. Okay, so you can think about this in the following way. It's like 7 divided by 2 is equal to 3. That's the number of times that 2 goes into 7 evenly. And then plus whatever's left over, which is a half. Okay? That's how you can think about this. So that's a full, all the way through example of a fairly complicated long division problem. And I made sure to use one with a remainder so that you could see this remainder here. So, yes, Sully?
Is the 4x, like, right before the bottom, it was like a plus and then it's a negative? Is it supposed to be that way?
Sorry, where?
Like, at the bottom?
You talking about here?
No, like when you're solving the problem. It goes from,
Here?
yes, like above that, it's a positive 4.
Ah, I see what you mean. So yeah, how did this go from being a positive 0x and a positive 4x to then I wrote negative 4x? Why did I do that?
This is a minus sign.
Because there's a minus sign and this is in the parentheses, right? Do you see that now?
Yes.
Okay. Yeah, so we got to be really careful about that minus sign. And we got to make sure that we always put these parentheses here, because if we don't subtract, we're going to throw our answer all out of whack. Any other questions on this one? Okay, this is probably like about as complicated as I would ever ask you to do on a homework or a quiz or an exam, okay? So it doesn't get much more complicated than that. We have so many steps. I mean, just look at them. Okay. So we just keep going and going and going and going and going until it works out. So really, it's not that bad. It's just that you have to do the same thing 4 times in a row and make sure that you keep track of all your negative signs, right? As long as you can do the one thing that you need to do one time, you can do it 4 times. It's no problem. All right, so let's talk about something else. Let me see what I have left to do. Oh yeah, that's right. Okay, so I think I have time to make it through this. Okay, so I mean, this is a theorem. Oh, this is an interesting theorem, actually. Okay, what does this theorem say? This theorem says that if you divide a polynomial by a linear factor, okay, by a linear factor, then the remainder is going to be f of a, okay? So what's interesting about that? What's interesting is, okay, so this is our f of x, right? This is our f of x. If we divide by x minus a, then we are going to get a polynomial, that's the quotient, and then I get the remainder divided by x plus 1, right? That's what I'm going to get at the end, okay? The point of this theorem is that the remainder is actually equal to f of a. Whatever we get if we plug in negative 1 into the function f of x. So let's see why that's true. We'll just do this quick long division. It won't take us long at all, now that we're experts. So let's do it. So I'm going to do this one quick, all right, so that you get an idea of how it's going to go once you gain a mastery of this. I know I need to multiply by 5x to get 5x squared. So I put 5x here. I subtract 5x squared plus 5x. So if I do that subtraction, these ones cancel, and I'm left with, well, if I take negative 7x minus 5x, that gives me negative 12x. And then the plus 2 comes down. Now I need to know, what should I multiply x by in order to get negative 12x? That's clearly the number negative 12. So I put a negative 12 here, and now I'm going to subtract whatever I get when I multiply negative 12 with x plus 1. That means negative 12x minus 12. So the negative 12x minus negative 12x cancel, and I'm left with 2 plus 12, which is 14. Yes? Okay, so my answer is 5x minus 12 plus 14 divided by the original divisor, x plus 1. And the claim of this theorem is that 14 is actually what you get if you plug in negative 1 into this function. Let's see if that's true. Well, if I plug in negative 1, I get 5 times negative 1 squared. And then I take minus 7 times negative 1. And then I get plus 2, which I think is what we would get is 5 plus 7 plus 2, which is indeed 14. So this is, I guess, useful if you want to check your answer, probably, is the main circumstance in which this would be useful. This remainder is going to be whatever you get if you plug minus 1 into the original function. All right, so that's kind of neat, I guess. I'm not sure how practically useful that is, other than to help you check whether your answer is correct. Especially because it only applies when the divisor is linear, right? If I'm dividing by x squared minus a, this is not going to be true. This won't be true if I divide by that. It has to be x minus a. So it's a very specific type of divisor. Any questions on the remainder theorem? All right, doesn't seem like there are, so let's talk about another theorem, which this one is really well and truly useless. Or actually, it's not well and truly useless. It's extremely useful, but I made this section so short because you already know this. We already talked about this in that big T, F, A, E, all those like 6 statements that were all equivalent, right? Okay, x minus a is a factor of f of x if and only if it is a 0. Yeah? If and only if it is a 0. We already talked about that with the x, what with the x cubed minus 1 divided by x minus 1, right? We already established x minus 1 is a factor of x cubed minus 1 because 1 is a 0 of the function or of the equation x cubed minus 1 equals 0. If I set the numerator equal to 0, the number which I plug in to get 0 would be 1. Okay. So that's the factor theorem. So next up is the rational zeros test. This is what I really wanted to get to. So what is the rational zeros test? This one, again, was invented by Descartes, I think. So I think, therefore, I am guy invented this rational zeros test, which says, okay, if I have a polynomial, okay, a n x to the n plus dot 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 dot, right? Then all of the zeros of this polynomial, which are rational, will satisfy the following. So if p over q is a 0, okay, where p and q are natural numbers, okay, p and q are integers, right? So things like -2, -1, 0, 1, 2, dot, 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 right? Whole numbers, but possibly 0 and possibly negative. So all of the rational zeros will have the following property. The numerator must be a factor of the number a0. And the denominator must be a factor of the coefficient an. Okay? So why is this useful? This is useful because it's not hard to list all of the possible rational zeros of a polynomial and check one by one whether they are zeros or not. Okay? That's how we can use this. So let's see how that works. Well, what we're going to do is basically list all the possible zeros by finding all of the factors of a0, finding all of the factors of an, and then dividing each one of them to find all of the possible zeros of this function. Once we have those zeros, why is that useful? Well, it's useful because if we want to factor a polynomial whose degree is higher than 2, so a polynomial like x to the 4 plus x cubed plus x plus 1, right? If we want to factor something like this, we only learned how to factor quadratics, or maybe higher as long as they were quadratic in form, or if they had a GCF, right? But now we can go to the true general case. We can factor polynomials of any degree that we like as long as we can guess some of their zeros using the rational zeros test. So let's see an example of how this works. So we are going to factor this cubic polynomial. This cubic polynomial. So how are we going to do that? Well, the name of the game is, first, I recognize immediately that this is not quadratic in form. Not only is it not quadratic in form, it does not have a GCF. Right? It does not have a GCF. So I'm kind of like SOL in terms of strategies of how to factor this, except for the one that I just learned. So let's see how it works in practice. Well, I know if P over Q is a 0, then P is a factor of 4, and Q is a factor of 3. Yes? So P, the numerator, goes with a0, and the denominator goes with an, which in this case is 3. So what are my options? My options are, well, let's list the factors of 4. The factors of 4 are 1, 2, and 4, right? 1, 2, and 4. We agree? How about the factors of 3? Just 1 and 3. What kind of number has factors that are just itself and the number 1? That's a prime number, right? Okay. So these are all of the possible numerators that I could have, and these are all of the possible denominators that I could have. So let's list all of the possible factors that are rational, or all of the possible zeros. So possible zeros could be any of 1 or negative 1. That would be what I get if I divide 1 by 1, yes? Or 1/3 or negative 1/3, because that would be what I get if I divide 1 by 3. Or 2 divided by 3, or negative 2 divided by 3, or 2 divided by 1, or negative 2 divided by 1. And then finally we have 4, negative 4, and then 4/3, and then negative 4/3, yes? Did I miss any? I should yeah, I think this is fine. I should have all of them here. Should be 8, right? It should be 2 to the 3. 2 to the 3. So this would be 2, 4, 6. Wait, what am I doing? Oh, because yeah, okay. I should have 16 or something like that. Wait, how many do I have here? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. That's... How is that making sense? Okay, it's because it's 2 times 6. I should have 6 unique numbers because I have 2 here and 3 here, so multiply 2 times 3, that gives us 6. We multiply times 2 because there's also a negative version of each one. So yes, this is the correct number of numbers to have. Anyways, the point of the rational zeros test is these are all of the possible rational zeros that could be a zero of this function. Okay? That could be a zero of this function. So I can check one by one whether they are a zero or aren't a zero by plugging them in. So let's see, for example, f of 1. What would I get? I would get 3 times 1 cubed minus 2 times 1 squared minus 6 times 1 plus 4. And that would be 3 minus 2 is 1, minus 6 is negative 5, plus 4 is negative 1. So, oh well, it turned out that 1 is not a zero. Okay, so what is my next step? My next step is to keep going one by one by one by one by one by one until I find one such that when I plug it in, I do get 0. And then I'll be happy. Sorry? Okay, so let's see, what could I plug in? Okay, I'm just going to tell you. I'm not going to repeat this process over and over and over again, but that's what you would have to do if you wanted to do this. But I'm just going to tell you that 2/3 is a 0. So let's see why. F of 2/3 would be 3 times 2/3 cubed minus 2 times 2/3 squared minus 6 times 2/3 plus 4. So what would that be equal to? Well, this would be 8 over 9, yeah? 8 over 9. And then this one would be 8 over 9 again, yeah? Because 2 cubed over 3 squared. And then the next one would be 4, minus 4, and then plus 4, which would be 0, right? Because these two cancel and these two cancel. So it turns out that f of 2/3 is a 0. So yay, we are happy. Why are we happy? Because our goal is to factor this. Why is it useful to know one of the zeros? Why is it useful to know one of the zeros if my goal is to factor this polynomial? Why is it useful to know one of the zeros if I want to factor? Yeah, if I know one of the zeros, I know one of the factors, right? In particular, I know that now that x minus 2/3 is a factor. And therefore, x minus 2/3 will divide evenly into f of x. What am I going to get if I divide a degree 3 polynomial by a degree 1 polynomial? I will get a degree 2 polynomial. And then I'll be able to factor that using regular factoring or quadratic formula. Okay, so let's take this all the way home. This is going to be miserable. I just want to let you know in advance, because of the 2/3, this is just going to be a nightmare. But let's do it. We shouldn't be afraid to do things that are scary. We should just try and see how it goes. Okay, we're going to do x minus 2/3, and inside, what am I going to have? I'm going to have my my f here, which paste, here we are. Okay, so starting line of this, oh, it's actually not going to be too bad. Okay, so first step would be to add in any missing places, but there's no missing places. It goes 3, 2, 1, 0. We're happy. We got them all. So now what do? I take the leading term of the divisor and I divide it by the leading term, the leading term of the dividend, and I divide it by the leading term of the divisor. All these D words mess me up. So what do I get? I get 3x squared, right? Okay, so what happens if I then subtract? I get minus 3x cubed minus, what is this? This times 3x squared is 2x squared. Right? Okay, so if I subtract 3x cubed from 3x cubed, these ones cancel, yeah? But actually, it also turns out these ones cancel, don't they? Because I'm subtracting negative 2x squared from negative 2x squared. I'm subtracting itself. Those go away. So these come down. We're left with 6x plus 4. So now what am I going to have? I'm going to have a plus sign. And then I need to figure out, what do I get when I divide 6x by x?
Isn't it negative 6?
Sorry, thank you. It's negative 6x. I copied it down incorrectly. So it should be not plus 6, but it should be minus 6. And then I get minus whatever I get when I multiply negative 6 with these terms, which would be negative 6x, and then negative 6 times negative 2/3 is positive 4, right? So now what am I left with? These ones cancel and these ones cancel, and my remainder is 0. I knew that the remainder would be 0 from the start because I knew that this is a factor of this. And I knew that x minus 2/3 was a factor because I know that f of 2/3 is 0. That is how I knew that this division was going to go so smoothly. So let me finish this. We still got 3 minutes here. Let me finish this. So what have I determined? I have determined that 3x cubed minus 2x squared minus 6x plus 4 divided by x minus 2/3 is equal to 3x squared minus 6. Yes, this is what I determined. Why is this useful for our end goal? Our end goal is to factor this expression, which if I move x minus 2/3 to the other side, I get 3x cubed minus 2x squared minus 6x plus 4 is equal to 3x squared minus 6, all being multiplied by x minus 2/3. Okay. Do you see the magic now of why this was a fruitful endeavor? It's fruitful because our goal is to factor a cubic. I don't know how to factor cubics. I know how to factor quadratics, so I rewrote the cubic as the product of a quadratic and a linear term. And now I can factor this guy pretty easily, right? I can factor that guy. I can take a 3 out, and then I'm left with x squared minus 2 and x minus 2/3. And how does x squared minus 2 factor? X minus something and x plus something, right? What goes in my blank here, and then we can be done? Minus 2 and plus 2 would be if I had x squared minus 4. Not minus 2 plus 1. It would have to be whatever the square root of this number is, right? So I'm just going to put square root 2. Okay, so this is the power of the division algorithm. I hope that after doing so many examples, you're starting to get a little bit better of a feel for it. But ultimately, the homework is going to be where you get your best practice. So we'll stop. This is not on the quiz. And we'll stop there for today. Have a good weekend and be safe out there, everybody.